For use as part of a talking picture, the sound to accompany the photographed action must be recorded for reproduction when the picture is shown. The most desirable material for this purpose has been found to be the photographic film. The finished film employed for reproduction in the motion picture theater, therefore, carries not only the picture of the action that is to be seen, as it did in the silent picture days, but also the photographic record of the sound that is to be. The sound and picture are usually photographed on separate films, which are called negatives. These negatives are combined by ordinary photographic printing to produce the positive print which is used in the theater to reproduce the original picture and sound. Since the photographic film is affected only by light, it is necessary for the recording of sound to convert the sound waves to corresponding changes in light. As I speak, the sound waves produced by my voice are transmitted through the air to the microphone, where these sound waves are converted to changes in an electric current. These variations in the electric current are then amplified and used to control the light falling on the photographic film. The light that falls upon the photographic film is in the form of a fine, bright line extending transversely of the direction in which the film moves. The part of the film on which the line of light falls to make the photographic sound record is called the sound track. When the line of light is so placed as normally to extend part way across the sound track, and the sound-controlled variations cause the position of one end of the line to move transversely of the track, a record known as a unilateral variable area soundtrack is produced. When both ends of the line of light are caused to move transversely of the track, a record known as a bilateral variable area soundtrack is produced. When the line of light extends completely across the soundtrack, and the thickness of the line is varied by the sound-controlled current variations, a record known as a variable density soundtrack is produced. All of these sound records contain photographic records of light variations corresponding to the pressure variations in the original sound. If either a variable area or a variable density sound record is run past a narrow line of light from a fixed source, and the light, after passing through the film, is visually observed, the amount of light reaching the observer is constantly varying from instant to instant. If the eye were capable of quantitatively measuring the light, it would see that the amount of light reaching it from either sound record varies in exactly the same way. There are in common use today electrical devices which will quantitatively measure what the eye can only approximate. The photoelectric cell is one such device and is universally used in the reproduction of photographic sound records. The reproducer system to which you are now listening contains such a photoelectric cell. This varying beam of light falling on the photoelectric cell produces variations in the electric current which are directly proportional to the variations in the light beam. As the varying electrical current in the photoelectric cell is small, a vacuum tube amplifier is required to increase it to the point where it will operate a loudspeaker. The loudspeaker converts the varying electrical current into sound waves, which are the counterpart of the sound waves falling on the microphone in the recording studio. To review, in the recording process, the original sound waves are converted to varying electrical current. The varying electrical current is converted to variations in a light beam, and the varying light beam produces a photographic sound record. In the reproducing process, the photographic sound record is used to produce a varying beam of light. The varying beam is converted into varying electrical current, and the varying electrical current is then converted back into sound waves. Since the advent of successful talking pictures in the late 20s, nearly all variable density photographic sound recording has been done by means of a device known as the light valve. The light valve contains two very thin metallic ribbons, tightly stretched and spaced very close together to form a light transmitting slot. These ribbons lie in a strong magnetic field, and the amplified sound current flows through the ribbons. The electric current reacts with the magnetic field, causing the ribbons to move like shutters, displacing them in direct proportion to the amplitude of the current. In order to ensure high-quality sound recording, the vibrating length of these thin ribbons is limited by bridges, over which the ribbons are tightly stretched. The tension of the ribbons is adjusted by tensioning means. The ribbons are so delicate and their separation and movements so slight that the action of the ribbons can be observed only with the aid of a microscope. The separation between the ribbons is actually less than a hair's breadth. A steady light, concentrated by a lens, passes through apertures in the magnetic pole pieces. This light is varied by the slot defined by the ribbons and is concentrated by another lens system to form a very fine line of light on the photographic film. Since the ribbons act as light-controlling shutters, any change in the sound current flowing through the ribbons will cause a corresponding change in the size of the light-transmitting slot, defined by their closely spaced edges, and therefore in the amount of light falling on the film. The device thus acts like a valve controlled by the sound current for controlling light. In the explanation of the light valve action that follows, attention will be directed particularly to the portions of the ribbons that control the light, and these portions and their movement will be shown schematically. In this schematic representation, it will be understood that the relative dimensions of the ribbons and the arrangement of their physical supports are illustrative rather than actual dimensions and arrangements. As has been explained, the ribbons lie in a magnetic field, and the amplified sound current flows through the ribbons. The electric current reacts with the magnetic field, causing the ribbons to move like shutters, displacing them in direct proportion to the amplitude of the current. A steady light is concentrated on the ribbons, and these ribbons, acting as shutters, cause variations in the light corresponding to the pressure variations in the original sound. This varying light causes variation in the exposure of the film. The exposed film, when developed and printed, is the sound record. The soundtrack used for the reproduction of music will be shown on the screen, and the soundtrack will be changed from a variable area to a variable density track simultaneously on both the picture and sound record. The photoelectric cell and the entire reproducing system is the same in all cases.